Security Seminar here at Purdue University. Today is my great pleasure to introduce Mike Burmester from Florida State University. He's going to talk about provable security in mobile ad hoc networks. And I saw some faces in the room that I know that they work in the area, so they'll be very interested in the talk. Just to give you a little bit of a background, Mike was previous with Royal Holloway, London University, got his undergraduate degree from Athens University and the PhD from Rome University. And his main research interests are in key distribution, privacy, anonymity, network security, and watermarking.
Thank you. My name is Mike Burmester, as Christina said, and this is joint work with Trifan Lee, who is also at Florida State University. He's a visiting professor there. And what I shall talk about is security for mobile ad hoc networks. This area has been sort of, a lot of research has taken place in it, and it's some very interesting work has been done, including work in Purdue, on designing efficient and reliable routing algorithms. The focus has been on efficiency and reliability, and not so much security. And this approach makes sense in a new area where you're not quite sure how to get things done. It's best to focus first on working out protocols that are reliable, and at a later stage, when you have something which works, then consider the possibility of it working securely and not being abused while it works. So, in many respects, I think the time has come to look at how these protocols can be secured, and in general how the whole area can be viewed from a security angle. And this is what I'm going to talk about. So one of the problems with security is that you have to sort of formalize your model before you can even start talking about security. And the model itself is not sufficient. You also have to formalize the model of the adversary. You have to very precisely explain or limit or describe what the enemy can do, what strategies the enemy can use. And that is sometimes referred to as the threat model. And then you also need another model. You need a security model, with respect to which you will prove your security. What is security? So I actually will need a formal definition for a mobile ad hoc network, a formal definition for the threat model, and a formal definition for my framework, security framework. And then I start asking questions. My first question is that, is it possible at all within my formalism to get security? Because if I can't, then I've put the security to be too tight, and then I can't get anything. And I will considering two ways of achieving my goal. There will be approximations. They will converge towards my goal. And the one will be a reactive approach, tracing malicious faults. And the other one will be a proactive approach, tolerating faults. And I shall say more when I come to that. My introduction is very brief. The mobile ad hoc networks, there's a lot of work going on, and I could spend a quarter of an hour talking about them. I just will sort of single out some of the basic properties they have. Essentially, they are sort of collections of mobile wireless nodes. They have no infrastructure because the nodes move and the range of their broadcast is short. The links are made and broken in an almost ad hoc way. Usually the nodes are battery powered, so they have constrained resources. To communicate in such an environment, it is not possible to communicate directly. What you have to do is you have to communicate by relaying packets through other nodes. So you have to find a route, and the packet is relayed from node to node until it reaches its destination. And the big problem there is how can you design a routing algorithm which is secure in a malicious environment. And the problem itself is ill-defined. I mean, the question is, what do you mean by secure in the first place? So you have to define a formal framework for security. And the second thing is, what do you mean by malicious adversary, which means that you have to describe what maliciousness or the threat model. So that's what I will start. But I need models. So my first model will be trying to capture the essential characteristics of a mobile ad hoc network. It has been done in many ways. Essentially, the first thing is I have to capture the nodes, the mobile nodes. What are the mobile nodes? And the simplest way is to use a finite state machine. So each, and a probabilistic one, they're allowed to toss coins. So my nodes are sort of Turing machines or whatever it is. This is from an abstraction. I need this abstraction because if I want to prove anything, I have to be very specific about what I can achieve and how I achieve it. The next thing is a little more complicated, but it can be done quite simply. How can I describe this network which keeps changing in time? And the simplest way is to use a finite again, a sort of state machine, but a random process. It's sort of a Markov process or whatever it is, and which at each point in time it specifies maybe I can use at each point in time what will be specified is a graph, which is the network, and the state of the system. So I don't know, can I do this? Oh, I can use the mouse. Thank you very much. So a graph G, in general, a graph GT, and the state ST. The state is the set of all internal states of the system. So GT will be on the vertex at V, and it'll have an edge set, and these edge sets keep changing because the links keep changing. And the ST is the sort of the internal states of the system. And this is not enough. I have to actually capture the particular way these graphs develop and the way. So I impose certain constraints which come in three categories. The first is the Markov constraint, the second is a mobility constraint, and the last is the medium constraint. The Markov constraint essentially has to do with memory. So what happens is the current state of the system, given the current state, then the next state is defined independently of all the previous states, earlier states. And the second one has to do with the transitional probabilities, how you go from the current state to the next state, the current state being GT, and the next state being GT plus 1. Or this is the system. And these are sort of done in a way which is independent of t, of the time. And then I just define these transitional probabilities as being essentially my mobility distribution. So networks, ad hoc networks, are defined by a mobility distribution. Who takes part in the mobility distribution are essentially the nodes and nature. The mobility distribution may be simulatable. Some of the ad hoc networks fall into this category, simulatable ad hoc networks, but most of the more interesting ones are non-simulatable. And the reason is that nature cannot be simulated, or you cannot simulate the behavior of the nodes. The nodes may have sort of non-simulatable behavior. If you could simulate, of course, the model would be much easier to deal with. What I'm trying to capture is a general setting, a more general setting, and the more general it is, the more closer to the applications I have in mind it will be. So whatever it is, if you don't want this definition, just the earlier definition will do, but I cannot prove anything if I don't have a reference point to which I'm going to prove things. And my next slide has to do with, I haven't finished this yet. The last constraints will come into the medium constraints. These are the normal, what you would expect a wireless broadcast constraints, to be. Namely that you want the sort of the medium to be promiscuous. If a node broadcasts something at some point in time, then all its neighbors will receive that at the same time. And essentially the time taken is bounded, so I want synchrony. I don't want this time to blow out of, get larger and larger. So I want the medium to be promiscuous. I want the medium to have synchrony. I want bidirectionality. I can do without. There are interesting models without, but to make life simple, let's assume that the graph is symmetric. And the last one, and I have to deal with this, has to do with limited bandwidth. In other words, if within a neighborhood, every node starts sort of sending out broadcasting, then what will happen is you will overload the medium, and you will have transmission failure. So these are essentially restrictions, constraints, as I call them, which somehow try to capture the behavior of a mobile ad hoc network, and I will be bound by these. And now I will be bound by these is, sorry, I've jumped a slide. I have to sort of be more specific about this. The constraints actually bound the behavior of the nodes which adhere to the rules of this system. But malicious nodes need not adhere to this. You cannot force nodes to have transmitters with a limited bandwidth, or to have weak, low battery, or use weak batteries. Malicious nodes may use other systems. So my model is not adequate in the sense that it has defined the behavior of, if you want, the good nodes, of those who stick to the sort of the rules of the system, but it doesn't specify the rules of the malicious nodes. So the threat model, that has to be defined separately if I want to deal with security issues, because security issues will have to deal with malicious behavior. So in particular with mobile ad hoc networks, what the malicious, since I want to capture this, I have to describe what malicious nodes could do, is in particular they could use out-of-system links. They could have a separate wireless system. They could have more powerful broadcasting devices or directional antennas, or covert channels. Let's use this general term. Covert channels which are not in the system. So my definition is complete. It's only half the story. The other half has to do with the threat model. So now I have to define what the malicious nodes can do. And the traditional way of dealing with such a problem is to have an adversary who can mastermind the attack, all the malicious nodes. So the way the adversary attacks the system is through certain nodes. So the adversary has control of some nodes, which I shall refer to as faulty nodes. And through these faulty nodes, the adversary can do whatever the adversary wants to do. For example, have the hidden channels, run attacks called wormhole or rushing attacks. I will come back to these later. They can vary the transmission range, direct the transmission range, so not everybody gets it, or worse, replicate. So the model I will use is due to Hurt-Maurer, and it's an extension of the so-called Byzantine threats model, and in which what happens is a certain set of subsets of the node space is singled out, and that set is called gamma. The sets of gamma are those that can be corrupted by the adversary. So the adversary at the beginning of the lifetime of the system can choose which set of nodes it will corrupt. Once it has chosen, it can't change its mind. It can't choose others. They are fixed for the duration of the system. This model is not a dynamic, it's a static model. There are variants of it which allow the adversary at regular intervals, or certain intervals, to be able to release some malicious nodes back into the honest world and take some others, and so change the set. But I'm using this model, the static one. So the adversary can choose which nodes to corrupt, the set of nodes to corrupt from the set gamma, and this is called a gamma adversary. And the adversary corrupts, undermines the functionality or frustrates the functionality of the system using these corrupted nodes. The Byzantine threats model is a special case of it, in which the size of these subsets is all upper bounded by some number k. Say if k is 3, then the adversary can corrupt up to any 3 nodes it likes. But once it has picked the 3 nodes, it's stuck with these 3 nodes. It can't change in this static model. In this, the other thing to complete the sort of this definition of the threat model, I just want to refer to the ways the adversary can attack the system. The attack one is passive, and the other is active. Passive is the sort of least sort of malicious way, or the most benign way. What the adversary just does is eavesdrops on what is going on in the network. So it just observes and listens. The active one is what I described before. The active one involves dropping packets, snooping, modifying, fabricating, whatever else. Whatever the adversary can get away with it, with whatever is allowed in the threat model, the adversary will do it. Why? Because it wants to sort of frustrate the normal sort of functioning of whatever is happening in the network. I call nodes which do these nasty things malicious or Byzantine. This is the general name. So now I have defined what happens, what a mobile ad hoc network is as a sort of Markov process of evolving networks. I have defined what the enemy can do, what the enemy is bound by, what the threat model is. Now I can define what I mean by saying that something is secure, an application is secure. The kind of applications I have in mind are distributed algorithms, and in particular, routing algorithms. So what is a routing algorithm? In routing algorithm, what you do is you try, one node tries to find discover a route to another node, and then use that route to send a packet node relayed through the nodes to the other destination. The process is a distributed process. Everybody's involved in it. Everybody's involved because the node, each node knows only its local neighborhood, its neighbors. It doesn't know, and it can't go beyond it, and therefore it has to find out from its neighbors what their neighbors are, and so on. So everybody has to participate, at least in that local area, helped out together to find the path. And once the path is found, then the nodes on the path have to forward every packet received to the next one down the path. And that's a typical distributed application. I will describe my sort of definition, security definition, in terms of a distributed algorithm, P. What I will, so this distributed algorithm, if you think about P as being, say, a routing algorithm, what it will do is it will be given as input the source and the destination and the packet that the source wants to send to the destination. It'll work a little bit. Eventually, that packet will have to travel to the destination, and the destination will have to send back an acknowledgement to the source. And if everything happens, then the source will be happy that the destination got the message, the packet, and the destination will have the packet, and the protocol will end in a sort of, it will terminate in a success state. So it'll say good, success. If that doesn't happen, if the source doesn't get an acknowledgement that the destination has received the message, then the protocol won't end in this state, won't be successful. And so my definition of security has to do with tolerance, tolerating a gamma adversary. So I'll say that this protocol, say this routing algorithm, whatever it is, P, tolerates a gamma adversary as defined just now, if the probability that the protocol terminates when the adversary is active is the same as the probability that it terminates when it's passive. And that means essentially that the adversary has not achieved anything. the protocol is equally likely, so the probability that it succeeds is unaffected by whatever the adversary does. So the adversary might as well stay quiet and not do anything. And that's sometimes called the sort of perfect tolerance, gamma tolerance. I may allow certain cases where the tolerance is not perfect, where there is a small error probability, so the adversary gains a little bit, but if epsilon is small, this is the next one, so it's less than epsilon, that means that what the adversary gains by taking part in this protocol, by being active during the sort of the execution of the protocol, is a little bit, but not enough to affect in any practical way the protocol. I can also talk about computational tolerance, and that is when the two probabilities are they're not equal, but you cannot distinguish them using polynomial time procedures. Just for practical reasons, this model differs, my approach differs from the traditional one, where you normally would want an application to be reliable. You would say that the protocol is reliable if it succeeds 100% of the time. In the kind of work I'm working here, even if it succeeds 75% of the times, that would be acceptable. In the real world, sometimes you could always convert a 75% to be almost 1. The question is, the cost in so doing may be very high, and if your nodes are bounded and all your resources are bounded, maybe you can just settle for 75% of the time. Okay, so now I'll get back to the kind of algorithm I'm working with. This is these are sort of these routing algorithms, which on which and a lot of work has gone on in this area, and most of the routing algorithms which have been sort of proposed have certain very advantages and offer certain. Some are more flexible in some ways, others in other ways. Essentially what you could do is you could classify them in two categories: those which are network-centric and those which are source-centric. Network-centric algorithms rely on the sort of rely on the algorithm in which the routing effort is distributed. Everybody helps out. So when you want to send something, what you do is you just send information about whom you want to send it, and your neighbors already have sort of vectors. They know how to send it forward. So it goes on without the sort of the source having to do too much work. The work is done on the way to the destination. There are a couple of algorithms in this category: DSDV, WR, and AODV. AODV sometimes falls in both categories. The second is the one in which the source does all the work. The source does the work to find out the best path, the shortest path to the destination, and the nodes on the way to the destination do the minimum. They just forward the message when they get it. From a security point of view, the source-centric routing is better, is less vulnerable to malicious attacks. And the reason for this has nothing to do with ad hoc networks. It's outside ad hoc networks. It has to do with the way trust is sort of trust infrastructures are linked together. So for example, if you want to do something and you want to do it in a secure way, the best way to do it is to do it yourself. You never delegate. The moment you delegate something, there is a risk that the person you have delegated to may be untrustworthy and may not do it. But if you do it yourself, then you can trust yourself. So the less trust you put in the others, the more secure in general, the less vulnerable the system is. Security mechanisms. The protocols one uses in distributed applications will always involve some crypto. And crypto comes in two flavors: symmetric key crypto and public key crypto. Symmetric key crypto is usually much cheaper. Public key crypto is more expensive. But there are cases when you have to do with public key, you can't use secret key. If you want digital signatures, it has to be public key. If you want to have a way in which your nodes can be authenticated in the system, you have to use digital signatures. So wherever possible, one uses MACs, message authentication codes. MAC here stands for message authentication codes, which can be used combined with a secret key to get what is called an HMAC, and that you can use for integrity checks in a limited way, and you could also use encryption schemes that way. So the problem with the digital signatures is comes in sort of it has not to do so much with the digital signatures. It has to do with a problem which public key crypto systems have, and I'll try to describe it. So the first thing is this. To be able to identify nodes in the system, at the beginning of the system, each node is assigned a secret key, is given a secret signing key, and also a list of the public keys of all the others. That's why I somehow avoid the trusted key infrastructures. So a node has kept a list of all the public keys of everybody else and its own secret signing key. So it can sign, and using the public keys of the others, it can verify everybody else's identity, for example, or link a message to an entity. So digital signatures then can be used to link messages which are signed by a node to the node who signed them. This all works perfectly well and keeps this kind of link, one-to-one link, except that in a malicious environment, if you have cheaters, they don't need to follow the rules. So what malicious nodes may do is they may start sharing their keys. So if there are 5 malicious nodes, they each share their 5 keys, and one malicious node now can present itself as 5 different people, 5 different nodes. And this creates a problem in a mobile ad hoc network, because the only way to deal with other people is through what you get from them. So if you get 5 signed messages by nodes who all claim to be your neighbors, you must assume that that is the case, whereas in fact only one node is there signing on behalf of the 5. This is sometimes referred to as the Sybil attack. So this is what one has to take this into account. This is one of the threats, and whatever secure protocols have to be designed, they have to be designed with this in mind, with this kind of threat in mind. And as I said, the problem is that you cannot link an entity uniquely, bind a physical node to an entity by using public key cryptography. This is not a problem of mobile ad hoc nexus, it's a problem of public key cryptography. You can't do it in any other way. If you decide to share your secret key with your wife, then your wife can pretend to be you if in this kind of wireless environment. There are 2 general attacks which can happen in this environment, due of course to the malicious behavior of the adversary. And I've grouped them into 2 categories, and most of all the attacks fall in these 2 categories. The so-called denial of service attacks and the man-in-the-middle attacks. Denial of service attacks are sort of the straightforward attacks. They are the attacks in which the adversary triggers some kind of event which results in the network not being able to provide the service it is supposed to provide. And usually this happens by flooding the network with irrelevant packets. That's malicious. Or it may happen in a non-malicious way where there are too many nodes in a neighborhood, and one node wants to talk to the others and just sends out in a flooding mode, broadcast in a flooding mode packets, and all the nodes sort of repeat that, and then you overload the network. So another one is packet dropping, and the most malignant form of this attack is the one where colluding nodes attack your distributed denial against a specific, mount a distributed denial of service attack against a specific node and isolate it. How to deal with these things? Well, you can use various ways. One is intrusion detection techniques. Well, if it's not malicious, there are nice ways of doing it using gossip protocols. These are protocols in which somehow reduce the redundancy in a clever way. If it's malicious, one way is to have denial of service, intrusion detection mechanisms. That doesn't work in general very well. A better one is to have fault tracing mechanisms and some kind of redundancy. So if something doesn't come from one path, it comes from another path. I'll talk about this more. The man-in-the-middle attacks are sort of more nastier because what the enemy does is the enemy sort of takes control of the communication between two nodes by interposing between them. So the nodes are not neighbors, but the enemy somehow gets close to the one and sort of through some other one close to the other. So it sort of then relays packets from the one to the other. If it's a passive attack, then the enemy just relays packets, nothing else. And that may seem harmful, harmless, except that because the enemy has taken control of the communication, the enemy at any point in time, if the message is sort of critical, can halt it, can stop it. And that would be a denial of service. And it's a smart denial of service. It is only there when there is a good reason, when the enemy wants to stop it. So the enemy, by having control of a communication channel, can actually prevent certain things happening when they would do most harm, for example, to the enemy. The active ones are even worse. The enemy then puts on a face. He's an insider, a respectable node, a node with a public key. Everybody knows it, but it misbehaves. And there are three attacks which I won't have enough time to describe, but they're all rather clever, and they all have disastrous effects on communication. They come under sort of different names. One is called wormhole, the other is called rushing attack, and the final one is Sybil attack. The wormhole attack is an attack in which two malicious nodes, what they do, use their special covert channel to communicate, and the one links up with the one system and the other, and they actually pass all the messages through the one, and so the two nodes which communicate through this channel of the malicious nodes may think that the route is very short, because essentially it could appear to them that there are only three nodes, or four nodes between, two nodes between them, the two malicious nodes, and actually the distance may be much longer. So they may prefer to choose this route, the path from other paths, because it's the shortest. It appears to be the shortest, the most effective, whereas it isn't. And it's under the control of the enemy. The rushing attack is a sort of twist of this. What happens is the malicious nodes can actually rush through the packets, through these covert channels, much faster than what happens in the normal network, and that gives them even more power. And the Sybil attack is the attack in which actually they share their secret keys, and a node can present itself to its neighbor as being 5 different nodes in 5 different faces, if there are 5 bad guys. How do you counter such attacks? Well, that's hard, and these are the hardest to counter. There are 2 out-of-system methods which are used. Sometimes these attacks cannot be solved, cannot be addressed within the system. And usually these are addressed out of the system. And the one is a temporal and the other is locational. The temporal deals with the time. Speed of light is that's your upper bound. The time it'll take to rush through this sort of packet cannot go faster than the speed of light. If you have very accurate timing devices, maybe you could do it. The second has to do with the location. If your neighbor claims to be 5 different people, then you may insist on getting authenticated, signed copies of this sort of position. And then each one will sign that position. But at the same time, somewhere far away, another malicious node will do exactly the same. Now, if you have 2 signatures of the same node, which one's in place 1, another 15 hops away, then that node is a lying node. And that's how you can deal with it. The security is typically dealt with in a protocol in different layers of the protocol stack. And there is a reason why, and why it can be done, and how it can be done, and why it can't be done in a sort of an arbitrary way. And this has to do with the fact with the faults that occur. So you have two essentially types of faults. Faults that are whose effect is stochastically indistinguishable from ordinary link failures. So they occur independently with a certain predictability. You know them. And they're not dependent. And they are caused by the mobility of the system, radio interference, the sort of thing when bulbs sort of have a life expectancy and they won't last too long, and you can design methodologies to deal with it by having 3 bulbs instead of 1, and when 1 goes out, then you replace it. And there are the other kind of faults which are not stochastically indistinguishable from ordinary link failures. The first type can easily be addressed at the medium access control layer by using the standard sort of error correcting or sort of ways, and that is used, and it's quite so. If a packet gets dropped, it gets dropped with probability say 2/3. Then you ask for it to come back. Well, with a high chance it'll come back. If it's maybe the second time it doesn't come back, but then the probability that the third time is much smaller, so you can deal with this. The malicious ones certainly cannot be addressed at that layer. So anything which has to do with malicious faults must be addressed at the protocol layer. One last, so that you cannot assume that the things will be sorted out at a lower layer and you won't see them. Some faults will have to be addressed at the higher layer. And just a remark here is that one of the nastiest attacks that the enemy can do is to hide behind this differentiation. So the system at the medium access control layer deals with faults which occur with the sort of predictable probabilities. And the enemy can mask an attack pretending to and using this probability. So the system will try to get the message at the medium access control layer. They will try to work it out, but this is much clever. Although it happens with a predictable probability, the probability it's not independent. It's very dependent on what happened in the past. So if you try to just get a sort of so the packet is dropped and you never ever get the packet again. So the system just works and runs and runs and runs. So that has to be addressed. As I pointed out at the beginning, there are a lot of good protocols which have been proposed in this area, and they're highly reliable. Some of them actually involve the people working at Purdue. They have been designed to be very efficient and very reliable. They were not intended to be in a sort of security framework, especially not with sort of the malicious type of attacks I'm talking about. And so it makes sense to try and, at this point in time, to find ways of securing them. And this is what I'm going to do. So, my problem. The problem is this. Is there a secure routing algorithm? And I have to be more specific, because now I have a model and I know exactly what I want. What I mean by this is there a routing algorithm that will deliver immediately or almost immediately the packet to the destination, provided, of course, that there is a path from the source to the destination which has no faults, no faulty nodes. Because if every path is occupied by the enemy, then there is no hope in hell of ever getting to the destination. And the immediate delivery has to do with the following. I don't want my routing algorithm to keep on trying. So it tries to find a path, it fails. Then it tries another one, it fails. That is not secure. There are applications in which you need to know the packet has to go immediately. If it doesn't go immediately, you may get all sorts of problems. The applications I have in mind, say, for example, are critical. infrastructure applications. So they may be a nuclear power station, something may go wrong, the message has to go out. If you stop it for 10 seconds, then you've had a disaster. So the answer is, of course, flooding works. Flooding will sort of seep through. If there is a nice path, it will find it. That's what flooding does. However, flooding is too costly. Flooding could trigger a denial of service attack if the network is very dense. So that's not enough. So let me reword my question. Is there a secure routing algorithm which uses as route a path and not the whole network? And the answer is no. There isn't. Why? And I will give you a very simple proof. It's nothing to do with this by waving my hands. So the question is there a reliable way of deciding a priori whether a node is faulty or not? And in my threat model, the adversary was allowed to choose at the beginning of the system, lifetime system, a set of malicious nodes. Now, there is no reason why the adversary will tell me which ones the adversary has chosen. That's part of the game. I mean, the nodes that are malicious are hidden, they're there, and they will only maybe later on be revealed. If there is any scheme of being able to discover what the adversary chose before the nodes exhibited or sort of did something wrong, then you would be able to guess what the adversary has done. So if there is such an algorithm which can find a path which has no faulty nodes, then you can use that same algorithm as a trigger to discover what the adversary, which set the adversary chose before the nodes did anything wrong. So you cannot a priori decide whether a node is malicious or not. You have to wait for the nodes to misbehave. So I will try to find two solutions to this problem. They are approximations. They converge to what I want. And the first one uses a reactive approach. The second one uses a proactive approach. The reactive approach is you capture the bad guys. You find the bad guys. If you find the faulty nodes, then eliminating the one at a time, what will happen, since the adversary can only choose a certain number, eventually the adversary will lose because he will lose all his sort of malicious, all his sort of nodes, and then the system will run perfectly because you won't have a malicious set, at least in this approach. The other one tolerates malicious behavior. It tolerates at some cost, and I will describe how it works. Before I do it, I want to quickly point out some of the problems one has when one tries to trace malicious behavior. So malicious behavior will be traced as follows. Nodes, good nodes, non-malicious nodes, will observe malicious behavior. What they will do is then sign a report, which report will say that node A signs below that node B is malicious, and the signature by node A. You get this. The question is, who is the faulty node, A or B? It could be that A is truthful in the statement and that B is malicious, or it could be that A is a liar. You can't say which one. So what you do is you throw away both. That's one approach. The other one is when you try to trace malicious behavior, one way is to actually look at failure reports. If things happen, if certain paths are more vulnerable to failures, then it may be more likely that there is a malicious node on these. That argument is good in some respects, but it can't be supported because what will happen is all these rates which are based on reports can be affected by malicious nodes lying and giving faulty reports or no reports at all. So I will focus on K adversary sets. This is the Byzantine threat sets. And the way I view the security is as follows. If I'm using tracing, then what you do is once you trace, you throw them away. Each time the number of bad nodes is lowered. Eventually you win that way. Another way would be to get more than K nodes, if you know what the threshold is, to countersign. So you would want a certificate by k plus 1 nodes to say that one node is bad. If you know that k is the maximum, then that's how you can get away with it. I'm not going to describe. I have two protocols here which are very nice. I'm not going to describe them. You can find them. I think I will post on the web page the paper.
So I have a question. Did you change the question with the immediate delivery? Because your approach is going to buy immediate delivery, right?
Not here. The other one, the multipath. So this one doesn't address immediate delivery. What it does is it says the following. It does address in the following. So let me point. So what happens is this. So I does address it, and I'll come to it. But thanks for pointing it out. I'll give you a minute. So this is called optimistic, and it's called optimistic because if there is no misbehavior, if no node misbehaves, then the cost is exactly the same as any of the other protocols. You don't pay any more. So this is why it's optimistic. In the honest case, with no faults, there is no extra cost. If there is misbehavior, there is extra cost to trace the misbehavior. And I'm just skipping them. The theorem will say the following. It says that, and it's provable. It's provable in the model I just described, the models I just described, that one of two things will occur. Either the packet will be delivered immediately to the destination, or if that doesn't happen, you will trace a faulty node. So you have one of two. Okay? So the protocol somehow in a clever way, so the packet goes from source to destination, and nodes don't do anything more than what they normally would do. But if something goes wrong, then there is a second. So it's a two-pass. Forward, downstream to the destination, upstream back to the source. Downstream goes the packet, upstream comes the acknowledgement. That's what you always need. Now, if there's misbehavior, the nodes use a special sort of the way it works is you have so I'll go back here. You have each node has a timer, and you count on the time it will take for a reply to come back. Something should come back. If something does not come back, something has happened. The nodes are instructed to always send back reports, negative reports. It's like nodes committing suicide, because such a negative report automatically has the effect by that the signer of the report and the reported failure node, they will be deleted from the system. So they are both, yeah?
I have a question about the use of negative acknowledgement. It seems to be like very difficult to prove that you did not receive a packet.
Oh, right. So that comes in the proof. What happens is that all these timers are set in such a way so that if failure occurs, the first one to click is the one which is next to the faulty node.
I know, but what I was trying to say is that you are using negative acknowledgement, which means that you did not receive the packet. So
no, you did not receive anything. You did not receive. No. You don't just do. You couldn't be malicious.
But if I'm malicious and I say that I did not receive, I can actually put the blame on myself.
That's correct. And what happens? This is suicide. You kill yourself and the next one. So a malicious node can commit suicide in order to kill the one downstream. So anybody can do it. I said the one of the two is malicious. I still win. The system wins whenever a malicious node, if a malicious node signs such a document, then it's a report, then the system wins, the adversary loses. Because the adversary, if it's one-to-one, the system wins on a one-to, if the system can exchange a good one for a bad one, then the system wins. We can talk to it offline. It's an interesting protocol. The next one is, I haven't got much time. And so what I wanted to point out, and I'll quickly do it here, is that this can easily be piggybacked, can be linked with existing protocols which do not offer the service. So AODV and DSR will certainly work in this way. So you just have to add it, and so you get the security, the reliability which AODV or DSR offered, plus the security in the sense that either the packet will be delivered or somebody will be traced. Possibly a malicious, a faulty node which just wants to cause problems. But if you capture a faulty node, that's good enough. I will quickly want to go over this adaptive multipath routing because it is interesting, and I think 5:20 is my deadline. So I take 5 minutes. So the question is this. It has been long sort of accepted that if you could send your messages over several paths, then if one fails, you have some backup. And this has been a good way of dealing it, but reliable, except it's approaching the spirit of flooding. Flooding does this in a sort of more complicated way, but it does too much of it. It has too much sort of redundancy. So if you could control the redundancy, maybe if not all broadcasts are part of it, but just those on vertex disjoint paths, maybe you can do better. All of the multipath routing algorithms are algorithms which find paths, several paths, and usually you just choose the first one. And after that, you dump all the others. What you do here is you don't. You continue and you build it up. But then what you do is when you broadcast, you use the first path you got. So adaptive multipath routing is actually single path routing to start off with. The adaptive part comes with the enemy provokes you. So if the enemy disrupts your path, then what you do is you pull out of the bag the backup paths you have, and you use a backup path. So you have all the others, but you don't use them. You use the first one, which is also the shortest one. The other ones are not used. They are only used if need comes, if there is a need. And the system this protocol is designed to adaptively, during time, change this and always come up with paths. And it builds up to a maximum size of paths. And the best application is the round robin one. So you have all your paths, which are vertex disjoint, at least from the view of the honest nodes. And what you do is you send and you have many packets to send. And you send each packet in a round robin way on the next available path. And if some is sort of broken, then you use it on the next one. And so essentially the cost is the same as single routing, except that you have to find multiple paths. But the approach for multiples, once you trigger an approach for a single path, more or less automatically you get side information for further paths, which usually you dump, and here you don't dump. So I think what I will do is I'll give to Christina the paper and you post it. Is there a web page? Sure. To post it? And because it is interesting. There's a lot of discussion here. It has certain nice properties. One of the nicest properties is that actually it can also be piggybacked on existing routing algorithms. So for example, or it can be combined with the tracing algorithm, so you can get that as well. It can be combined with DSR to get a sort of adaptive DSR. So DSR also finds some more paths, and you can use the more paths. And that's it. Thanks for your patience. Please, yeah, go ahead.